So I will be talking about my work, which basically is a follow-up on my PhD thesis, which I did with Bob Cohn, and recently I did some small progress with my former postdoc. Okay, so I apologize, there might be some people who already heard this talk recently, but okay, hopefully they will learn something more or understand more today. Okay, so what's the question? So we are talking about wrinkling of annular sheets. So let me first start talking a little bit about the sheets, a little bit benefiting from what Bernd said before. So okay, so we are talking about thin objects like sheet of paper or schematically sketched here. So of course we see that when we are trying to deform thin objects, they relatively resist the stretching. But if we try to compress them, that gets quite easily. And there is, of course, a reason for that. And the reason is that, well, there are basically two-dimensional objects. The third dimension is very, very, very small. And when we are trying to compress them, they relax or they respond to this compression by going out of plane. So using that there is one more dimension. And also, of course, using the fact that since they are very thin, it's very easy to bend them. We'll come to that later. Okay, so we'll use a variational framework, meaning we'll write down the energy of the system and try to minimize the energy and try to say something about the minimizers. So let me a little bit explain what energy do we consider. So as Bernd was mentioning, you know, one can, I mean, when one formally starts with a finite elasticity and try to derive what are the limits of this energy, or what are the kind of theories which can describe that, of course, the first thing is to say, okay, actually, how big these deformations are, or what kind of deformations there will be, meaning, you know, how the energy scales, and depending on this, one gets different energies. So now I'm gonna a little bit cheat at this level, and I will combine basically outcomes of two of these different theories, meaning that I will consider the situation where I'm thinking about the object which is formally two-dimensional. So I think I have originally a flecked object, which is then deformed, and the deformation is described by basically mapping from the 2D to the 3D, saying what is happening to the mid-surface. Okay, and I'm now trying to compute what is the energy of this deformation. And this energy will consist of two parts. The first part is so-called membrane energy, basically telling us that if we locally stretch the sheet, we need to pay the energy. If we would locally compress the sheet, we'll need to pay the energy. If we locally just rotate it, so a rigid motion is cost-free, right? So that's exactly this first term, where which one sees that it's non-negative and it's minimized, or actually it's zero at all the rotations, and it's strictly positive away from the rotations. And there is a second part, so-called bending energy, which is penalizing the fact that, you know, I can still make an isometric immersion of the object, but still I will pay a little bit the energy. And the reason is that, okay, it's very thin, but it's not infinitesimally thin, meaning that if I would have a mid-surface, which will be isometrically mapped, there is still upper part which would be a little longer and the bottom part which would be a tiny bit shorter. And of course, that stretching or compression costs a little bit of the energy. But the thinner the sheet is, the less it costs. And that's reflected by this h square in front. So h for the talk will be the thickness of the sheet, same as here. Okay, so there is h friend in front, and formally, or one could say it's basically penalizing, or it's cost of the curvature. Okay, so one specific example, that's basically what I did in my PhD thesis, was that we looked, I don't have such paper here, but we looked at the annular thin sheet. So you can schematically draw here. There is a picture from the experiment. So we have a thin sheet, which is, you know, sitting on, let's say, some substrate, water or so, which is stretched in the radial direction. So stretching out, stretching in, which is schematically shown by these arrows. And now what's happening? So, okay, I will try to show it here. So I have the sheet, which it can be rubber sheet or so, which we stretch in the radial direction. And now what is happening is that in this inner stretching is strong enough, then some of the circles near the inner radius will be pushed towards the center, right? I mean, if I stretch it in this towards the outside, then I stretch it towards the inside. Some of these, some of these circles near the inner ones will kind of be pushed towards the center, meaning they will be pushed into less space. They will be forced to accommodate less space. And as we can see here, one option how to do that is going out of plane. But of course, they can't do it completely freely, because if they go out of plane, they can't go too much out of plane, because then the sheet would be stretched even more in this direction, which it doesn't like. Okay, so now let me talk a little bit about so I try to explain what's the setting, and let me now talk a little bit about the methods, or the kind of strategy, or the achievement. So this problem, as one can see already at the level of the energy, is a non-convex variational problems. So it's kind of, the first question already one asks is, okay, what can we actually say? You know, what should be actually the question, right? We are trying to minimize the energy, which is non-convex. So possibly there are many critical points, or local stable equilibria. So which one we are actually trying to get? So one can say, okay, we'll try to really get the global minimizer, or to find it or describe, which is very difficult. So, but as a first step, we can at least try to say, okay, but what will be at least each energy? In particular, how will it depends on this small parameter h. Our goal is to see what's happening when the thickness of the sheet goes to 0. And the outcome is the following. So we prove that when we are trying to minimize the energy, we get this type of scaling law. Now let me explain a little bit what it means. So we are trying to minimize this energy. And so at the leading order, one is thinking, okay, when I would now formally send h to 0, what am I getting? So formally, one would say, okay, this term drops out, but actually it's a little bit more complicated, because of course this part is not logarithmic continuous, so we need to relax this part as well. And in this particular situation, what would happen is that we get a small plus here, meaning we would just look at the positive parts of that. And this is very standard. This is a very general theory. Basically, it's a theory of relaxation. In the mechanics community, it's called tangent field theory, and it basically predicts that, okay, in this formal limit, you know, how will the situation look like? How will be the kind of macroscopic deformation? In this situation, it will say, okay, in this region, there will be wrinkles, which is a way how to relax the compression, but it will not say much about the wrinkles, or basically nothing. And minimizing this relaxed functional will give us the E0. So that's the leading order. And then we say, okay, but actually we don't have h equals 0. So when h is positive, small but positive, there should be a compensation for that, and that's this next order term. So this linearly scaling h is basically the cost of actually having the wrinkles there. Okay. So for the rest of the talk, I will try to explain a little bit different model and different example, and that's a little bit again related to what Manu was saying. So now the situation is the following: we consider again circular thin elastic sheet, but now sitting on top of a sphere of some substrate which is curved. Now this is important. So it's a little bit different what you were saying, but in your case you were not on a substrate, but you had kind of intrinsic mismatch. Here it's not the case. Here the sheet is nice flat, it likes to be flat, but now it's kind of sitting on a substrate, and there is a kind of, the delamination is not allowed, so it really sits on it. And of course, as far as this is the picture, this is a kind of zoom in picture, and as far as the curvature of the substrate is not very large, or it's either not very large or the sheet is relatively small, it more or less stays on the pole, kind of relatively flat, so nothing is happening. But of course, now if we are assuming that the sheet is either large or the curvature is increased, it's happening exactly what you were describing, right? That the geometric effects somehow, I mean, it's not allowed to wrap a curved let's say, spherical substrate with flat sheet, right? I mean, geometry doesn't allow that, so, I mean, it has to respond. And the way the response is, again, by wrinkling. Now, what's happening is the following. So if I would, so looking from the side, this is my substrate, and here I have my spherical sheet. And now if I'm thinking, okay, originally the sheet was sitting on the top flat, and now what I'm forcing the sheet is to wrap the substrate. And now it has basically, if I would be looking in this radial direction, it has basically two, well, in extreme I would say two options. So one option is it really wraps, really kind of, this length will really wrap around the top. But of course, what is then happening is that the circle which was here around is now forced into a circle which has a little bit shorter diameter, which means it has to compress. The other option, I would say, okay, I want to preserve the length of the circles, so I will just simply project it down. But of course, in this situation, I will need to stretch the sheet. So the truth, as we will in the next picture, is something in between. So what energy do we consider? So here we'll use a even more simple Fepel-von-Karman energy, which is kind of small slope, small deflection regime. So U will be the in-plane displacement, Xi will be the out-of-plane displacement. So this is corresponding to the membrane energy. This is basically measuring the bending, the curvature. This corresponding to the bending energy. And then, in addition, compared to the first example, I have the substrate, which is penalizing, which basically wants me to be close to the spherical shape. And on top of it, it's also penalizing if I would be wrinkling. You know, it will cost a little bit because the moment I wrinkle, the substrate has to also deform. Now, a few words about what substrate do we consider and what are the scalings. So Ben was also talking a little bit about the scalings, that normally you have the membrane term has H in front of it, that's basically the volume. The bending has H cubed in front of it, and normally the substrate term shouldn't have any H. The reason is clear because the substrate doesn't care how thin the sheet is, right? I mean, it's the cause of the deformation which we prescribed. That's the boundary condition, and it doesn't care. So normally we would have H cubed, and H to 0 here. So we can normalize by H, giving us no H here, H squared, and 1 over H here. But we have 1 over H squared, and the reason is the following. So we are thinking, or the model we looked at was the model of elastic substrate, for which if we are, using a simple model, we can say, okay, if it were be, large compared to the thickness of the sheet, or could say infinite, the cost of the elastic energy, the substrate, the elastic energy of the substrate can be in some simple approximation written as a H1/2 norm of the boundary conditions which we prescribe. So the honest way would be H2 minus 1/2 times the H1/2 norm. Now, when we wrote this paper, the idea was to kind of approach the physicists because it was also motivated by some theoretical works in the physics community, and they don't like these norms because they are non-local, they are hard to work with, and so on. So what they like to do is to replace them with so-called Winkle foundation, which is actually the L2 norm. So one can do that, or at least formally, but of course then one needs to, L2 norm scales differently than H1/2 norm, so one needs to compensate for this kind of formal move. So we did that, and that's the source of this H-2 norm, H-2 scaling, okay? A few more words. The solid substrate only penalizes the out-of-plane displacement, so it allows the slip. And compared to some of the theoretical works where they had H2 minus 1, because they were considering a liquid substrate. So they originally started with this Winkle foundation. Okay, so this is the energy. So what's the result? So the result is the following. We again minimize the energy, and again we subtract the kind of relaxation of the problem. But here the situation is a little bit more complicated, as we'll see in a second. And the statement is that, okay, to the leading order, it's the energy is behaving like some minimum of some simple energy, which is written here. We'll talk about that in a second. And we can also say something about the next order. And the next order is, unfortunately, we don't have the matching scaling, but it's between a linear in H and H log H. Okay, so let us now talk a little bit about this F0. So this F0 in the previous problem was really just the relaxation. So just saying, okay, bending doesn't matter, and compression is for free. Now here it's a little bit more difficult or more complicated, and the reason is that in this situation, compared to the previous, in contrast to the previous one, is that all three terms have the kind of the same scaling. As one can see here, okay, we have no derivative here in xi, but we have h2 minus 2. We have one derivative, h2 0, and we have two derivatives and h squared. So somehow formally, all three terms behave or live at the same footing, and this is really the case. And what happens in the end is that all three terms at the leading contribute to the leading order, which was not the case previously. And this kind of leading order term can be well explained in this situation. So it's a scalar one-dimensional problem. So it's just describing this radial, what's happening on one radius. And the unknown is V. V is the in-plane displacement, and it's exactly basically having two terms. The one is the radial stretching. That's the one saying, how much we need to stretch the sheet in order to kind of accommodate the fact that along this curved surface we are a little longer. So that's the first term. And the second term is the cost of wrinkling. That's saying if we have this circle which we push into a little bit less space, how much this will cost. What's interesting compared to the previous works is that the cost of wrinkling already enters at the leading order term. Okay, and this cost of wrinkling can be easily computed. It's written here. Basically, so eta is the amount by which we need to compress it. When eta is positive, that means we need to stretch it, or minus eta, we need to stretch it. Of course, there is nothing more to do than just stretch the sheet. And when it's negative, but a little bit more negative than 0, then it starts to wrinkle and behaves linearly. So this the red part is the graph. Okay, and it can be easily derived by considering a one-dimensional problem. Okay, so basically I already did the discussion of this function. So it describes the leading order energy. The cost of wrinkling is entering here. That's the cost of azimuthal wrinkling. What's interesting is that from this cost of wrinkling, one can immediately compute what's the optimal length scale of wrinkle. And it turns out that this optimal length scale in this particular problem is independent of the location. That means the moment we have wrinkles, we know what's the optimal length scale, which will be important in 5 minutes. Okay? But this dominant energy in particle does not include two contributions. One contribution is the cost of changing the wave number. So one can say, okay, why do I need to change the wrinkling if the wrinkling length scale is constant? But the problem is that one has these kind of circles along which we want to wrinkle. And of course, if I have let's say the length scale would be 1, and I have a circle which has length 10, that means I have 10 wrinkles. And then I go a little bit farther, and I get to a circle which has length 15, meaning ideally I would like to have 15 wrinkles. So the question is, okay, how do we go from 10 to 15? That's not obvious, and of course it will cost some energy. So that will enter the next order. And the other one is also the cost of somehow, I call it discreteness of the wave numbers. That's again, let's say the optimal length scale is again 1, but now I'm at the circle which has length 11.5. So of course we need to make a choice. So do we have how many wrinkles we'll have? And since it will be not really exactly 1, we'll pay a price for that. So here I'm repeating the statement. And so, in order to prove this, we need to show both the lower bound and upper bound, meaning the upper bound means we need to construct for each H a good competitor. For lower bound, we need to really show that no matter what we do, we will always have this type of energy. So very quickly about the lower bound, which usually is more difficult in this situation, is not that much involved. So what one does is just rewrite the energy using the radial coordinates. Not important, you don't need to look at this. Important thing is that you get basically this thing, which after some work can be rewritten into this kind of leading order functional. And then we have remainder. Remainder is written here. Again, not important what's there. Important is that all of the terms have a sign. All of them are non-negative. So at the level of the lower bound, we drop this RH, we throw it away, and just work with what's written here. And with a little bit of playing, we somehow show that we can get the lower bound. Okay. So now let us talk a little bit about the upper bound, which is usually not that involved, because what one can do is say, okay, we look at the experiment, we look how the deformation look like, and we try to write down this deformation and compute the energy, and if we are lucky, then it works. So in this situation, it's not that easy. And one of the issues is that, when I'm trying to do the upper bound, I need to show the other inequality, meaning I need to show that, okay, the real energy is well approximated by this, and on top of it, all these non-negative terms which we threw away in the lower bound, we now need to argue they are harmless in the situation, meaning that in the upper bound, we need estimates for all of them showing that they are not important. And it turns out this is not that trivial, and the main issue is that it's not clear in what way one should interpolate, or how should one go from one circle to the other, how should one, in what way one wants to change the wrinkles, how one wants to go from 10 to 15. So there is a kind of very natural and easy, naive idea which says, okay, say I would have 10 wrinkles at this circle and 20 wrinkles at this circle. So I say, okay, I will kind of interpolate between these two wave numbers. So in the middle, I will have combination of these two wave numbers, and I will interpolate in a way that somehow it works. So it turns out this doesn't work, and it turns out that in this situation, the upper bound, which we want to have H log H, will be of order 1. So it's completely out. So then there are other ideas which says, okay, maybe we can, okay, and there is one reason why this is so, and the reason is the following, that when we have, say 10 wrinkles here and 20 wrinkles here, if we are trying to have an arc length parametrization running around the circle, we need to have a little bit of in-plane displacement, which due to the periodicity of this construction is relatively small. On the other hand, where it's purely just one wave number, it will be also small. But the problem is that in the middle, where we interpolate between them, it will become large, because somehow it will push the material too much out. And this is the reason. So the other idea is, okay, maybe it's not good to have, just one wave number here and more wave numbers there. Maybe we can have all the time combination of wave numbers. So this helps a little bit with this shear term, but makes a mess for the other terms. But after some optimization, we got this H log H term. Actually, originally we had a kind of, in this upper bound, we had a funny term which was like H times exponential of a square root of log with a minus, which is basically function which grows slower than any polynomial function, but it grows faster than a log function. And with some optimization, we improve it to the log. But it was surprising that in upper bound, we got some crazy function. Okay. So a few comments. One can also study the situation where this substrate, this rigid or rigid elastic substrate is not that rigid. So one has a beta, which is beta less than 2, and one can try to look what's happening in this situation. So in this situation, formally, since in this situation, the cost of wrinkling is cheaper and cheaper. In the limit, here we would have an isometric isometric immersion, and it will be a little bit different story. Few comments, or just one comment. There are other problems, other wrinkling problems where one can study the scaling laws and try to get a little bit of understanding of them. To mention one, with Bobcon, we look at the so-called drape problem, where one considers a hanging drape, which has a fine wrinkles prescribed on top, and let it hang down. Of course, the sheet doesn't like the wrinkles, it tries to relax, and then one asks, okay, in what's the rate of relaxation, how fast it happens, and although it actually prefers to get a little bit wider. So the scaling law sheds a little bit of light on this. So my time is almost over, so let me wrap up. So we consider variation a viewpoint. H as a thickness was a small parameter, was regularizing the problem, this non-convex variational problem. In this specific example or setting on the sheet on a sphere, what's kind of different to other problems is that the leading order already entered this. So the wrinkling contribution already entered the leading order energy, and the next order contribution was just related to the cost of changing of these wrinkles. And in this other moment, when we have a softer substrate, there the stretching becomes subdominant. It's so-called, in the physics community, they call it inverted tension field theory. Okay, thank you very much for your attention. So of course one can of course model. The question is, what can one prove? I'm not sure. So of course, in this situation, the radial geometry is important, right? So of course, in what you are saying is, your material will kind of distinguish between the directions, right? So if it were very strong, then it would not, you would not have circles anymore. You would have a less symmetric situation. I don't know. So I mean, of course, as long as it's not very strong, you would expect you have a similar situation. The moment it's very strong, I don't know what would be the answer.
In paper industries, really things like that, curl also play a role, and might be of interest to consider this anisotropy.
Okay.
Other questions then? Yeah? Will you do something similar if you start from 3D elasticity instead of focusing carbon?
I can imagine. So actually, in the first problem I talked about, which I did in my PhD, in that situation, we also, so the first our argument was for like 2D model, and then there was a question, okay, but I mean, I can't arrive to such combination of two energies by kind of reducing the dimension, but one can basically repeat the argument starting from the 3D elasticity. In that first, I mean, we did it, that's in the paper. In this other one, we didn't try because, I mean, it was for physicists and they don't care about it, right? I mean, they don't appreciate, 30 pages more just saying that, oh, it works also for finite elasticity. So we didn't try. I would say, why not? But it's a lot of work, of course. But I mean, for example, in this first problem, one needs to say, okay, now I have a, originally the argument was for basically plane to something, so kind of on a level of surfaces. So then you say, okay, my finite dimension, so with finite thickness sheet, you kind of write it as a surface is part of the argument you kind of do for each surface separately, and then you need to combine by the standard, Frieseke, James Mell, and so on. So, I mean, there we did it. Here, I would imagine one can try to do that. But too much work for, I would probably say, not surprising answers.